The next speaker is Miss Rhea Palak Bakshi. She is a graduate student at George Washington University, and she is an expert in knot theory. And I would like to mention she is an author of a new upcoming book in knot theory. So we look forward to the book. So Rhea will talk about a tour of Skein modules. So over to you, Rhea.
Thank you so much. Hello, everyone. My name is Rhea Palak Bakshi. I would like to start by thanking the organizers for giving me the opportunity to speak at this conference. So today I'm going to be talking about Skein modules, and I will be giving an overview of the main results and the major developments that have taken place in the theory of Skein modules over the last 3 decades or so. So what is a Skein module? Well, for that, let's go back a little bit in history. So J.W. Alexander discovered his polynomial, which is now known as the Alexander polynomial, in 1928. And he also noticed that the links, when he defined this polynomial, satisfied some sort of linear relation. And then in 1969, John H. Conway rediscovered this relation, which he called a Skein relation, and he normalized this polynomial, and this gave rise to the Alexander-Conway polynomial. And for many years, this was the only polynomial link invariant for links in S3. Up until 1984, when Warren Jones discovered what's known as the Jones polynomial. And this polynomial has origins from seemingly unrelated theory of von Neumann algebras in functional analysis. But the discovery of this polynomial served as an impetus for the discovery of other polynomial link invariants in S3. For example, the Homefly-PT polynomial, which was discovered in 1984. The Kauffman polynomial, the Kauffman two-variable polynomial, the Kauffman bracket polynomial, the Dubrovnik polynomial, which was also discovered by Kauffman a few months later, and the Vasilyev-Gusarov invariant, which was discovered in 1989. So what all of these have in common is that they're invariants of links in S3, and they have a defining Skein relation. So if you want to develop invariants of links in any arbitrary 3 manifold other than S3 built on these Skein relations, then that is where Skein modules come into play. So Skein modules were introduced by Josip Chititsky in 1987 and independently by Vladimir Torayev in 1988. They are 3 manifold invariants, and there are many different Skein modules. And what all of these Skein modules try to do is that they try to capture some information about the manifold to which they're associated based on the kind of knot theory that that manifold admits. And the reason why we have so many different Skein modules is because you can take the links in the 3 manifold to be oriented or non-oriented, framed or unframed, up to homotopy or up to isotopy, and so on. But what all of these definitions have in common is that they generalize the Skein theory of all of these polynomial link invariants, like the Homefly-PT polynomial, bracket polynomial, Jones polynomial, for links in S3 to arbitrary 3 manifolds. So Skein modules are generalizations of all of these polynomial link invariants in S3 to arbitrary 3 manifolds. Why are Skein modules important? Well, over time, Skein modules have become important tools in low-dimensional topology and quantum topology. They have connections with many fields of mathematics, a few of which are algebraic geometry and hyperbolic geometry via SL2C character varieties and the quantum Teichmuller space. They are related to the Witten-Reshetkin-Torayev invariants. They are used in the combinatorial definition of these invariants. They're related to topological quantum field theories. You can categorify Skein modules to get homological invariants of 3 manifolds. They're related to representation theory, quantum cluster algebras, Templey-Lieb algebras, Hopf algebras, Hecke algebras, and this list is not complete. So there's a lot of rich structure here. And because of all these connections to all these fields in math and all the interesting properties that these modules have, I don't think I need to motivate anyone that this is a very interesting subject to study. So here's the outline for my talk. I'll begin by giving some examples, basic examples of Skein modules, and I'll state some main results. But the bulk of my talk is going to be focused on the Kauffman bracket Skein module. So I'll talk about properties of Kauffman bracket Skein modules. I'll give some examples. I will speak about Witten's finiteness conjecture, and then I'll move on to Kauffman bracket Skein algebras. I'll speak about the positivity conjecture, state some properties, and then finally, time permitting, I will talk about the connection of Kauffman bracket Skein modules and algebras to the SL2C character variety. Okay, so before I start, I would like to fix some notation for the rest of the talk. M3 will always denote an oriented 3 manifold. L with an arrow will be the set of ambient isotopy classes of oriented links. LFR will be the set of ambient isotopy classes of unoriented framed links. LFR with an arrow will be the set of ambient isotopy classes of oriented frame links. And these sets may have the empty link. And we will always work with the commutative ring with unity, which may or may not have an invertible fixed element, which will be either A or Q. And FGB will denote an oriented genus G surface with B boundary components. So the first Skein module that I'd like to talk about today is the signed Skein module. So how do we define this Skein module? Well, we consider ambient isotopy classes of oriented framed links, and we take formal linear combinations of those of oriented links, and we'll take formal linear combinations of those links over a ring R, and then we'll mod out by the submodule that's generated by this following Skein relation, L plus minus L minus. So after modding out by this submodule, the resulting module is called the signed Skein module. And we denote it as S plus minus with an arrow. And it has some interesting properties. The signed Skein module of an oriented 3 manifold is a free module over homotopy classes of links in the manifold. It admits a natural algebra structure whereby you can define the multiplication of two links by, so L1 times L2 is just going to be the disjoint union. And the multiplicative identity of this multiplication is the empty link. And moreover, this algebra is a commutative algebra, and it's isomorphic to the polynomial algebra with coefficients in R, and the set of variables is the set of conjugacy classes of the fundamental group of the oriented manifold that you're working with. So this is the first most basic example of a Skein module, the signed Skein module. Let's discuss the Q deformation of the signed Skein module, also known as the framing version of the signed Skein module. So how do we define this? Well, we consider formal linear combinations of oriented framed links in an oriented 3 manifold over this ring of Laurent polynomials with the indeterminate Q. And then you consider the submodule, which is generated by these two relations. The first Skein relation, which is L plus minus Q square L minus. And the second is the framing relation, which is L1 minus QL. And L1 is a link which is obtained from L by twisting the framing of L by one positive full twist. So once you have this submodule and you mod out by this submodule, the resulting is the framing version of the signed Skein module, which we denote as S plus minus with F and an arrow on top. And in 1997, Josip Trubitsky showed that if the manifold that you're working with contains a non-separating two-sphere or a torus, then the framing signed Skein module has torsion. And later, Ove Kaiser showed that torsion occurs only in these cases. So this is sort of the first example which shows that Skein modules say something about the geometry and topology of the 3 manifold. And in this case, they detect non-separating two spheres. Turns out this isn't the only manifold that this isn't the only Skein module that does that. So here's the framing Skein module. So we consider unoriented framed links, ambient isotopy classes of this, and then we take formal linear combinations over the ring of Laurent polynomials in the indeterminate Q. And then we mod out by the submodule, which is generated by the framing relation L1 minus L. And then once we mod out by this submodule, the resultant is the framing Skein module S0. And we proved very recently that the framing Skein module detects the presence of non-separating two spheres in an oriented three manifold. And the main theorem that we used, and this is joint work with Diony Ibarra, Gabriel Montoya Vega, Josip Chutitsky, and Deborah Weeks. We proved this last year in December. So we showed that if an oriented three manifold contains a non-separating two sphere, which a framed link intersects either once or twice, and if the link intersects the non-separating two sphere twice, then it's once each by a different component of the link. Then an ambient isotopy of the three manifold changes the framing of that link only by an even number. And this change of framing is given by the Dirac trick. So in the first case, when the link intersects the non-separating two sphere once, we have the Dirac trick for a knot. So you have a component of the link which intersects the knot exactly once. And then this sequence of ambient isotopies gives this diagram on the left. And we see that the framing of the link has changed by +2. And in the second case, when the link intersects the non-separating two sphere twice, once each by a different component, we have this sequence of ambient isotopies, which gives this diagram on the left. And what we see is that the framing of this component has changed by +2. And interestingly enough, the framing of this component in green has changed by -2. So this theorem was the key result needed to prove the following result for framing Skein modules. And the result is that the framing Skein module detects the presence of non-separating two spheres by way of torsion. And in particular, it satisfies this formula. This is the torsion part. And we take the direct sum over all unoriented framed links which intersect the non-separating two sphere transversely at exactly 1 point. So the framing Skein module is another Skein module which says something about the geometry and topology of the three manifold. In particular, it tells you whether the manifold has non-separating two spheres embedded in it or not. Another such Skein module is the q-homology Skein module. This is also known as the q deformation of the first homology group. And we define it as follows. So we take oriented framed links and formal linear combinations over this ring of Laurent polynomials in the indeterminate Q. And then we take the submodule, which is generated by the Skein relation, L plus minus QL naught, and the framing relation, L1 minus QL. And then once we mod out by this submodule, the resulting module that we get is known as the q-homology Skein module, which is denoted as S2 FR with an arrow. And in 98, Josip Chutitsky showed that this Skein module is a free R module if the manifold is a rational homology sphere or if it's a compact submanifold of a rational homology sphere. Moreover, he showed that the presence of non-separating closed surfaces in the three manifold yields torsion. So this is an example of a Skein module that detects all non-separating closed surfaces which are embedded in the three manifold. Okay, so the next Skein module that I want to talk about is what's known as the third Skein module. So we consider formal linear combinations of ambient isotopy classes of oriented links over this ring. And then we take the submodule, which is generated by this Skein relation, V inverse L plus minus VL minus Z L naught. And then we mod out by this submodule. And the resulting Skein module that we get is known as the third Skein module. And if you all noticed, this Skein relation is actually the home-fly-PT Skein relation. So this Skein module is also known as the home-fly-PT Skein module or the Jones-Conway Skein module. The home-fly-PT Skein module of the solid torus was first computed by Jim Hostey and Mark Kidwell in 1987. And in fact, this is what led Joseph to discover Skein modules. And this was independently done by Turaiv in 1988. Some basic examples: the home-fly-PT Skein module of S3 is this ring, and the empty link is a generator of the module. In 92, Joseph Chutitsky showed that the home-fly-PT Skein module of surface I bundles has an algebra structure, which is isomorphic to the symmetric tensor algebra over conjugacy classes of non-trivial elements of the fundamental group of the surface. And moreover, he showed that this algebra is an involutory Hopf algebra. This was first conjectured by Turaiv in 1991. And then in 2001, Adam Shikara showed that the home-fly-PT Skein module of an oriented three-manifold is related to the algebraic set of SLNC representations of the fundamental group of the manifold. So we've discussed the framing Skein module, we've discussed the q-homology Skein module, the third Skein module, and we can in general define the Kth Skein module. And this is defined as follows. So we consider formal linear combinations of oriented links over some ring R, which have these elements R0, R1, all the way till Rk minus 1. And then we consider the submodule, which is generated by this Skein expression, R0, L0 plus R1, L1, all the way till Rk minus 1, Lk minus 1, where the links R0, L1, all the way till Lk minus 1 are illustrated here. So L1 is obtained from L0 by twisting, and then for L2, you twist more, and then you keep adding more and more twists. And then after you mod out by this submodule, the resulting Skein module is known as the Kth Skein module. And so from this example, you see that as k increases, as the value of k increases, we will get more and more complex Skein modules with more and more complex structure, which will say a lot of new things about the oriented three manifolds that they are associated to. And in fact, this example shows that there actually is an infinite collection of Skein modules that you can associate to a three manifold. All right, so there are many other important Skein modules that we can talk about, but due to shortage of time, I won't, but I've listed them here. They all have very interesting properties. The second Skein module, the homotopy and q-homotopy Skein module, are some examples. The fourth unoriented Skein module is another example. The Vasilyev-Gusarov Skein module, it's the Skein module that generalizes the Vasilyev-Gusarov finite type invariant. The Kauffman Skein module and Dubrovnik Skein module are some other examples, and these two are actually very interesting because when Kauffman discovered the Kauffman two-variable and the Dubrovnik polynomials, he showed that there's a substitution which makes both of the polynomials equivalent for links in S3. But as it so happens, these two Skein modules diverge when we work with links in length spaces. So these two Skein modules are not equivalent in length spaces, even though they are equivalent in S3. This was shown by Maciek-Mrczkowski. The next one is the Barnetton Skein module. So this Skein module involves Skein relations between surfaces in three manifolds. And this Skein module arises very naturally from Barnetton's construction of Khovanov homology. There is also an approach to four-dimensional Skein modules using approaches by Kamada and Kawauchi. So this is not a complete list of all the important Skein modules, but I thought I'll mention some of the important ones that I have been studying. So this brings us to the Kauffman bracket Skein module. This is the most extensively studied Skein module of all, and it has some very interesting structure and properties. Okay, so how do we define this Skein module? Well, you consider formal linear combinations of ambient isotopy classes of unoriented framed links in an oriented 3 manifold over this ring, which has an invertible element A. And then you consider the submodule, which is generated by the Kauffman bracket Skein relation, L plus minus A L naught minus A inverse L infinity, and the trivial component relation. And then you mod out by the submodule. And the resulting structure that you get is what's known as the Kauffman bracket Skein module, which we denote by S2 comma infinity. So some remarks are in order. In this Skein module, we have the following framing relation, L1 minus A cube L. The reason for this is that the Kauffman bracket polynomial is an invariant of regular isotopy. It's not invariant under the Radameister 1 move. And for simplicity, when we work with the ring of Laurent polynomials, with integer coefficients, we will use a simpler notation for the Kauffman bracket Skein module of an oriented 3 manifold. So this is an example of a skein or an element in the Kauffman bracket Skein module of the thickened annulus. So we have this element in this link in the thickened annulus, and then using the Kauffman bracket Skein relation, we can resolve this crossing. And then using the trivial component relation, we can resolve this component. And then what we finally get is an element in the Kauffman bracket Skein module, ax square plus negative a minus a raised to negative 3 times the empty link. And x over here represents the homotopically non-trivial curve in the annulus. So this is an example of an element or a skein in the Kauffman bracket Skein module of the thickened annulus. All right, so let's discuss some properties of Kauffman bracket Skein modules. So these were proved by Josip Chititsky in 1987. The first is that if you have an orientation preserving embedding of 3 manifolds, then that embedding yields a homomorphism of their Kauffman bracket Skein modules. Second, if you have a manifold which is obtained from another by adding a 3 handle to the second, then the associated embedding yields an isomorphism of their respective Kauffman bracket Skein modules. And if you have a manifold which is obtained from another by adding a 2 handle along a simple closed curve on the boundary of the second manifold, then the associated embedding yields an epimorphism of the Kauffman bracket Skein modules. And moreover, the kernel of this epimorphism is generated by 2 handle slidings. So 3 handle addition gives rise to an isomorphism of the Kauffman bracket Skein modules, whereas 2 handle addition gives rise to an epimorphism of the Kauffman bracket Skein modules. Next, if you take the disjoint union of 2 oriented 3 manifolds, then its Kauffman bracket Skein module is the tensor product of the Kauffman bracket Skein modules of the individual manifolds. And Kauffman bracket Skein modules satisfy the universal coefficient property. And in particular, if R and R prime are commutative rings with unity and you have a homomorphism between them, then the identity map on LFR, which is the set of all ambient isotopy classes of unoriented framed links in the 3 manifold, then this identity map on LFR induces this isomorphism of R prime and R modules. The following theorem, which was proved by Joseph in 2000, is very important. It states that if you have 2 compact 3 manifolds, oriented 3 manifolds, and if you work over the field of rational functions in the variable A, then the Kauffman bracket Skein module of the connected sum of those 2 manifolds is the tensor product of the individual Kauffman bracket Skein modules. So the reason why this result is important is because if you want to find the generators of the connected of the Skein module of the connected sum, then knowing the generators of the individual Kauffman bracket Skein modules, it gives us the entire answer. And in fact, this is going to be important when I discuss Witten's finiteness conjecture later on. Okay, so now that I've mentioned some properties, let's talk about some computed examples for Kauffman bracket Skein modules. So the first one and the simplest one is the Kauffman-Brackes Skein module for S3. It is the ring of Laurent polynomials with integer coefficients in the variable a. And the empty link is a generator. The Kauffman-Brackes Skein module of the surface I bundles, this was computed by Joseph Kwiatkowski in 1987. And he showed that this Skein module is a free module and is generated by the empty link and links in F which have no trivial components. So we will keep talking about Skein modules of surface I bundles in this talk. The reason being that the study of these Skein modules is sort of the first step of understanding the Skein modules of any arbitrary 3 manifold. The reason being that you can project the links in this manifold onto the surface and then work with the link diagrams. So we will talk about surface I bundles a lot in this talk. In 1989, Jim Hoste and Joseph computed the Kauffman-Brackes Skein module of length spaces when p is greater than or equal to 1. And they showed that this module is a free R module, and it has the floor of p by 2 plus 1 free generators. The next year, they filled in the gap for when p equals 0, and they showed that the Kauffman-Brackes Skein module of S1 cross S2 is an infinitely generated module. And in fact, it has this formula. And we see that it has a lot of torsion. And this torsion actually reflects the presence of the non-separating 2 sphere in S1 cross S2. So the Kauffman-Brackes Skein module is another example of a Skein module which detects the presence of non-separating 2 spheres in an oriented 3 manifold. Okay. So next we have the classical Whitehead manifold. Its Skein module was again computed by Hoste and Kwiatkowski in 92, and they showed that this Skein module is infinitely generated. It's torsion free, but it's not free. Tangley in 2006 computed the KBSMs of the exteriors of 2 bridge knots, and special cases for these had been computed earlier by Doug Bullock and by Lofaro. Patrick Gilmer in 2007 computed the KBSM of the quaternionic manifold and showed that this Skein module is finitely generated over the ring of Laurent polynomials in the variable a, localized by inverting all the cyclotomic polynomials. And the basis of the Skein module consists of 5 elements. Okay. Next, we come to S1 bundles over surfaces. So in 2009, Miotych-Dubkowski and Maciek-Miczkowski showed that the Kauffman-Brackes Skein module of the S1 bundle over the pair of pans is an infinitely generated free R module. In 2016, Carrega showed that the Kauffman-Brackes Skein module of the 3 torus over the field of rational functions in the variable A has 9 generators. And later, Patrick Gilmer showed that these generators are linearly independent, hence forming a basis. Then in 2018, Patrick Gilmer and Gregor Masbaum showed that the dimension of the Kauffman-Brackes Skein module of S1 bundles over surfaces is at least 2 raised to 2g plus 1 plus 2g plus 1. And then the next year, Detcherry and Wolf gave a precise answer for this, and they showed that for any compact closed-oriented surface F, whose genus is greater than or equal to 2, its Kauffman-Brackes Skein module is finite dimensional over the field of rational functions in the variable A, and its dimension is 2 raised to 2g plus 1 plus 2g plus 1. So this is more or less a complete list of all the computations that have been done for Kauffman-Brackes Skein modules. I believe there is some work that's been done on computing the Skein modules for prism manifolds by Maciek-Miczkowski, but that's probably the only example which I haven't discussed here. So the question that arises is that we have all of these examples. Do Kauffman-Brackes Skein modules have some sort of defined structure for all of these examples? And the answer is yes. So this was conjectured by Edward Witten, who's a theoretical physicist and Fields medalist. The conjecture is that the Kauffman-Brackes Skein module of any closed oriented 3 manifold over the field of rational functions in the variable A is always finite dimensional. And this was conjectured sometime in 2014 or 15. No one knows why, when exactly, because this conjecture has never been mentioned in any published work by Witten himself. The first written documentation of this conjecture was in a paper by Carrega in the year 2016, where they computed the Skein module of the 3 torus. And this conjecture was resolved in the affirmative last year in August by Gunningham, Jordan, and Safronov. And one of the tools that they used was the theorem by Joseph about the Kauffman-Braque Skein module of the connected sum of 3 manifolds. All right. However, this conjecture does not hold when we work with the ring of Laurent polynomials in the variable A. And the shining example is the Skein module of S1 cross S2. It is infinitely generated. So the next question that arises is that, is there any particular structure or any defined structure for the Kauffman-Braque Skein module over this particular ring? And in 2019, Marché conjectured the following. He conjectured that if you have a closed compact 3 manifold, then there exists an integer d and finitely generated R modules nk, such that the Kauffman-Braque Skein module of that manifold splits into the free part, or the direct sums of the free part and torsion part, so into cyclic modules, where these nk, they are a to the k minus a to the minus k torsion modules for each k. So Marché conjectured that the Kauffman-Braque Skein modules of closed compact 3 manifolds have this structure. So a byproduct of Detcherry and Wolf's work on the Kauffman-Braque Skein module of S1 bundles over surfaces shows that if we work over this ring, then the Skein module always has a to the k minus a to the minus k torsion for some k greater than or equal to 1. This result also holds, this conjecture also holds for the Kauffman-Braque Skein module of S1 cross S2. However, this conjecture is not true in general. This was proved by me this year in February. The Kauffman-Braque Skein module of the connected sum of 2 copies of the real projective space is a counterexample. This is based on work by Maciek Myszkowski from 2011, when he showed that unlike the Kauffman-Braque Skein module of S1 cross S2, this Skein module does not split as a sum of cyclic modules. So what we have is that all of the examples that I stated before, they all satisfy Marché's conjecture. But the moment we come to connected sums of 3 manifolds, we have this outlier over here. So the next question that one can ask is, okay, is there some defining structure for the Kauffman-Braque Skein module of connected sums of 3 manifolds? And to answer that question, the first step would be to investigate the Kauffman-Braque Skein modules of the connected sums of Handlebodies. So in the year 2000, Josip Pshititsky stated the following theorem. So he stated that if you have a disk with n holes, f0, n plus 1, and you consider the handle body Hn, so Hn is a genus n handle body, which is the I bundle over f0 n plus 1, then this Kauffman-Braque Skein module of Hn connected sum Hm is equal to the Kauffman-Braque Skein module of Hn plus m, so an n plus m genus handle body, modded out by an ideal which is generated by expressions of the form zk minus a to the 6 uzk for any even k greater than or equal to 2. And these zk's are just links without contractible components. And they intersect the disk which separates Hn and Hm transversely at k points. So the geometric intersection number is k. So uzk is just a modification of zk as shown, and we get this relation from the 2 handle slidings illustrated over here. So this theorem was stated by Joseph in the year 2000, and it was published. However, he did not provide a proof. And as it so happens, we discovered that this theorem is incorrect. And the counterexample is given by Hn connected sum Hm, where n is greater than or equal to 2, m is greater than or equal to 1. And we showed that the ideal should be replaced by a strictly bigger ideal to obtain the equality stated in the theorem. So what we did was that we analyzed 2 Handel slidings, and then we showed that you need more Handel slidings than stated in the theorem on the previous slide. And this just illustrates a curved system in H2 connected sum H1, which leads to the counter example. What we do conjecture, however, is that the theorem is true for H1 connected sum H1, and proving that result is work in progress. Okay, so this was all about the Kauffman-Bakshi Skein module and its structure and its properties and some examples. So now we move on to the Kauffman-Bakshi Skein algebra. So this is where surface I bundles are important, because the KBSM of only surface I bundles in most cases can be enriched with an algebra structure. And in this case, the empty link serves as the multiplicative identity, and you define the multiplication of 2 links, L1, L2 as follows. So if you have L1 times L2, you just place L1 over L2 in F cross I. And then you mod out by the Kauffman-Bakshi Skein relations, of course. And so we denote this algebra by SA, F cross I. And again, if we're working with the ring of Laurent polynomials with integer coefficients, we will use a simpler notation. We can generalize this to some unoriented surfaces, very few of them. And in that case, we will work with twisted I bundles over those surfaces. I will give one example of unoriented surfaces as well. Okay, so this is an example of the Kauffman-Bakshi Skein algebra of the torus. So if you want to multiply the curves 1, 0 and 0, 1, we place 1, 0 over 0, 1, and then we mod out by the Kauffman-Bakshi Skein relations to get this sum. Okay, so a few remarks. If A, the variable A is plus or minus 1, then for any 3 manifold, the Kauffman-Bakshi Skein module is always an R algebra. And you can define the multiplication of the links to be simply the disjoint union. And this multiplication is always commutative, associative, and it has the empty link as the multiplicative identity. If you have an embedding of oriented surfaces, then this induces a homomorphism of the corresponding Kauffman-Bakshi Skein algebras. And in fact, this is a really interesting property, which says that it is possible for I bundles over non-homeomorphic surfaces. So it is possible that I bundles over 2 non-homeomorphic surfaces, F1 and F2, are homomorphic. For example, the once punctured torus and the pair of pans. So these 2 surfaces are non-homeomorphic, but the I bundles are homomorphic to each other. And in this case, the Kauffman-Bakshi Skein modules are isomorphic to each other, but the Kauffman-Bakshi Skein algebra depends on this I bundle structure. So the Kauffman-Bakshi Skein algebras are not isomorphic to each other. So this is a really interesting property where Kauffman-Bakshi Skein modules can be isomorphic, but the algebras need not be isomorphic. And this is really important because when you categorify Kauffman-Bakshi Skein modules of surface I bundles, the categorification for the KBSM of the once punctured torus and that for the pair of pans are non-isomorphic to each other. So they're not the same. So this in fact tells us that when you categorify, you're actually not categorifying the Skein module, but rather you're categorifying the Skein algebra. All right, so let's discuss some examples of Kauffman-Bakshi Skein algebras. So first we'll discuss some commutative cases. So that means Skein algebras which are commutative. So this was proved by Doug Bullock and Joseph in the year 2000. They computed the Kauffman-Bakshi Skein algebra of the thickened sphere, show that it's isomorphic to the Kauffman-Bakshi Skein algebra of the thickened disk, which is isomorphic to the ring of Laurent polynomials in the variable A. They show that the Kauffman bracket Skein algebra of the thickened annulus is isomorphic to this polynomial ring, where X is the homotopically non-trivial curve on the annulus. And the Kauffman bracket Skein algebra of the pair of pans cross I is isomorphic to this polynomial ring, where X, Y, and Z are the three homotopically non-trivial curves illustrated as follows. All right, so some remarks. Chebyshev polynomials of the second kind, S sub I of X, they form a basis for the Kauffman bracket Skein algebra of the thickened annulus. And how do we get this basis? We just replace each component of the link with SIX, where X is the homotopically non-trivial curve. And this method of replacing links with Chebyshev polynomials is known as threading links with Chebyshev polynomials. This is important when I discuss properties of Skein algebras. All Skein algebras of thickened surfaces are commutative if the surface is a genus 0 surface and the boundary components, the number of boundary components is less than or equal to 3. And of course, if the Kauffman bracket Skein module of, the Kauffman bracket Skein algebra of a thickened surface is always commutative when A is plus or minus 1. So these are examples of some commutative Kauffman bracket Skein algebras. Next, we come to some non-commutative cases. So this was proved by Doug Bullock and Josip Pshititsky in the year 2000, where they computed the Kauffman bracket Skein algebra of the thickened torus and the thickened once punctured torus. They showed that for both of them, the Skein algebras are generated by the curves 1, 0, 0, 1, 1, 1, but then you mod out by these equations. So for the once punctured torus, you mod out by equations 1, 2, and 3. And for the torus, you mod out by the equations 1, 2, 3, and 4. This is known as the long relation of the Skein algebra. All right. So this brings us to the celebrated product to sum formula for the Kauffman bracket Skein algebra of the torus. So in the year 2000, Charlie Froman and Razvan Gelka showed that the Kauffman bracket Skein algebra of the thickened torus is isomorphic to a subalgebra of the non-commutative torus. And they did that by giving a complete description of the multiplicative structure of this Kauffman bracket Skein algebra. And they did that by giving a really nice product to sum formula for the multiplication of curves. And the elements that they used to obtain this product to sum formula are Chebyshev polynomials of the first kind. So they are defined recursively with initial conditions T0 x is 2, T1 of x is x. So what they did was that they replaced the variable of the Chebyshev polynomial with the torus curve. So let's see how they did that. Say you have two integers p and q and the GCD is 1. Then you let p comma q denote the PQ torus curve. Now, if the GCD of p and q is some number d, which is not necessarily 1, then you define p comma q sub d to be the dth Chebyshev polynomial in the variable p by d comma q by d. So what you've done is that you have replaced the variable of the Chebyshev polynomial with the p by d comma q by d torus curve. So one example of this is, say for example, we have 8 comma 2 sub t. Well, the GCD is 2. So you get the second Chebyshev polynomial in the variable 4 comma 1. And then using the recursive relation, we get that this equals 4 comma 1 square minus 2 times the empty link. And this is an element of the Kauffman bracket Skein algebra of the torus. So what Froman and Gelka showed was that if you have a PQ torus curve and an RS torus curve and you multiply them, then you get this really nice sum. Okay, so a couple of years ago, we at GW decided to investigate the multiplicative structure of the Kauffman bracket Skein algebra of the four-punctured sphere. So the four-punctured sphere was the next candidate after the torus to investigate the multiplicative structure because it's closely related to the torus. And in particular, you obtain the four-punctured sphere from the torus by hyperelliptic involution. So on the torus, there's a well-defined way of drawing curves, but how do we draw curves on the four-punctured sphere? So for this, we use Dane-Thurston coordinates. So what we do is that we take the 4 punctures on the sphere, and if I want to draw the curve 3, 7, I draw a grid, which is 3 by 7. And then I start from the bottom left corner, and I draw a straight line with slope 1. And then once I reach an edge of the grid, I reflect behind like a pillowcase until I reach this edge, then I reflect in front, then behind, front, behind, front. And I carry on until I hit another corner. And then I can deform these dotted curves and pull them outside of the grid. And then the curve that I get over here, this is the core of the curve 3, 7, which is illustrated in D. So with this method of drawing curves, we have the following theorem due to Doug Bullock and Josip Chititsky. They showed that the Kauffman-Braque Skein algebra of the 4-punctured sphere is generated by the curves 1, 0, 0, 1, 1, 1, and also by the boundary parallel curves, which we denote by A1, A2, A3, and A4. And in the year 2018, this is joined with Sujoy Mukherjee, Josip Chititsky, Maritania Silvero, and Xiao Wang. We provided an algorithm to compute the product of any 2 elements in the Skein algebra, and we gave explicit formulas for some infinite families of curves. This algorithm is based on the action of the generators of the mapping class group of the 4-punctured sphere on the basis elements of the Skein algebra, and we also use an adapted version of the Euclidean algorithm. So the mapping class group of the 4-punctured sphere is PSL2Z semi-direct product with Z2 cross Z2. And so we have the PSL2Z action on the basis elements of this Kauffman-Braque Skein algebra. And this action, PSL2Z action, is encoded by the Faraday diagram. This is a very pretty diagram, as you can see. It has some very interesting properties, and some of which are that any 2 fractions are connected by a curvilinear edge if and only if the determinant is +1 in the upper half of the plane and -1 in the lower half of the plane. And another interesting property is that if you have this curvilinear triangle, and you know that the fraction, so you know the fractions of at the end of the long curvilinear edge. So if you want to find the 3rd fraction at this vertex, what you do is just add the numerators separately and the denominator separately, and you get the fraction. So this is known as the Faraday diagram. I won't say much about it, but this features heavily in the algorithm that we provided. I'll be happy to discuss this later on if someone wants to. Okay, so this brings us to the positivity conjecture for Skein algebras. So a basis B for the Kauffman-Braque Skein module, for the Kauffman-Braque Skein algebra of surface I bundles over the ring of Laurent polynomials is positive if the structure constants for the multiplication lie in the ring of Laurent polynomials with a non-negative integer coefficients. So what that basically means is that if you have xi and xj, they're elements in the basis, then the product equals this sum, for which ak is in this ring and xk is in the basis. So the question which arises is which bases of the Kauffman-Braque Skein algebra of surface I bundles are positive? So this question was first posed by Falk and Goncharov in 2006 when they were working with cluster algebras. And to this end, Dylan Thurston in 2015 proved the following. He considered a normalized version of the Chebyshev polynomials of the first kind. So he just tweaked the initial conditions a little bit, but the recursive relation remains the same. And he said that if R is the ring of integers and A is 1, then this sequence of Chebyshev polynomials is positive on any surface. Moreover, he conjectured that this sequence of Chebyshev polynomials is positive for the ring of Laurent polynomials in the variable A. And evidence that this conjecture is true comes from the product to some formula for the torus, which I stated before, because we get that the Chebyshev basis that they constructed is positive. And moreover, for the 4-punctured sphere, in our case, the algorithm and the data that we have suggests that this Chebyshev basis is positive. So to this end, Tangley, Dylan Thurston, and Yu in 2019 showed that if the Kauffman-Brackes Skein algebra of a surface that has at least 4 punctures or its genus is at least 1 has a positive basis, then this basis is bounded below by this normalized Chebyshev polynomials of the first kind and is bounded above by Chebyshev polynomials of the second kind. Okay. Yes, so the last example for Kauffman-Brackes Skein algebras that I want to talk about, this is the non-oriented case. So if you consider the Kauffman-Brackes Skein module of L21, so L21 is a length space. It is an oriented 3 manifold. Then this has an algebra structure. And in fact, the algebra is isomorphic to this right-hand side, where alpha denotes the orientation preserving curve in RP2. So L21 is isomorphic, it is homomorphic to RP3, and RP3 minus a ball is it is homomorphic to the twisted I bundle over RP2. So their Skein algebras are isomorphic to each other. So this is the only example or one of the few examples of Skein algebras over twisted I bundles of unoriented surfaces which has been computed. Okay, so in the last 10 minutes, I would like to discuss properties of Kauffman-Brackes Skein algebras. Hopefully, I'll be able to reach to SL2C character varieties. So we saw that the Kauffman-Brackes Skein module of surface I bundles is infinitely generated, but the Skein algebra is in fact finitely generated, and the minimal number of generators is 2 raised to the rank of the first homology of F minus 1. This was proved by Bullock and Joseph and Adam Shikara. Joseph and Adam Shikara also showed that if the ring that you're working with is an integral domain, then the Kauffman-Brackes Skein algebra is always Noetherian. They showed that if the ring that you're working with has no 0 divisors, then the Kauffman-Brackes Skein algebra has no 0 divisors. And this in turn implies that if the ring has no nilpotent elements, then neither does the Kauffman-Brackes Skein algebra. So this is important when I discuss the connection to the SL2C character variety, this statement about nilpotent elements in the Kauffman-Brackes Skein algebra. For unoriented surfaces, Joseph and Adam Shikara showed that if you have an unoriented surface with even negative Euler characteristic and you consider the twisted I bundle over this unoriented surface, so basically the 3 manifold has only even number of projective planes embedded in it, then the Skein algebra of this twisted I bundle has no 0 divisors, provided R has no 0 divisors. However, this result does not hold for the Klein bottle. They also showed that the center of the Kauffman-Brackes Skein algebra of the thickened surfaces, this is a subalgebra. This is generated by the boundary components of the surface. So for example, in the 4-punctured sphere, the center of the Skein algebra were the 4 boundary curves, A1, A2, A3, and A4. They commute with all other elements of the Skein algebra. All right. Now, if we replace this variable A with the complex root of unity, then threading the links with Chebyshev polynomials gave rise to this theorem by Charlie Froman, Kanya Bartosinska, and Tangley, where they showed that if F is a finite type surface, meaning it's a closed connected oriented surface with finitely many points removed, then the Kauffman-Brackes Skein algebra of the surface I bundle over this field with the variable A is finitely generated as a module over its center. So the moment we have complex roots of unity, then the center is not only generated by the boundary components, but is generated by a larger class. Okay. So I think I have time to discuss connections to the SL2C character variety. Okay. So just some basics before I state the theorem. An SL2C representation of the fundamental group is a homomorphism rho from the fundamental group of the manifold to the special linear group SL2C. The character of a representation is this composition chi sub rho, which is the composition of the trace function with rho. A closed algebraic set X in Cm is the common zero set of an ideal of polynomials in this polynomial ring. And if you quotient this polynomial ring by the polynomials that vanish on this X, then what you get is the coordinate ring of X. So we will denote the set of all characters by X of M3. And for any element in the fundamental group of the manifold, we will consider a function T sub gamma going from the set of these characters to C. So with this setting, we have the following theorem due to Kuller and Shalin from 1983, where they showed that there exists a finite set of elements gamma I in the fundamental group such that every T gamma, which I stated on the previous slide, is an element of this polynomial ring. And they use this theorem to prove the following, that if every T sub gamma is an element of this polynomial ring, then the set of characters is a closed algebraic subset of C sub M. So we will now denote the coordinate ring of X of M3 by Rm3. Then Rm3 lies in the algebra of functions from X of M3 to C. And now we are ready to state the theorem by Doug Bullock from 1997. He stated that if we have a linear map phi sub tilde from CLFR, so this is formal linear combinations of unoriented framed links with coefficients being complex numbers, into this algebra of functions, and this linear map sends each knot to the negative of its naturally induced function, and each link to the product of the images of its components, then this linear map phi tilde descends to a map of algebras phi from the Kauffman bracket Skein algebra of the three manifold over C. A is -1, phi from this Skein algebra to this algebra of functions. And moreover, the image of this map is the coordinate ring R of X, and its kernel is the ideal consisting of nilpotent elements of the Kauffman bracket Skein algebra. So this theorem gives an explicit connection between Kauffman bracket Skein algebras and the SL2C character variety. Now, if you remember the theorem which Joseph and Adam Shikara proved about the nilpotency of Skein algebras, the theorem stated that if the ring contains no nilpotent elements, then the Kauffman bracket Skein algebra contains no nilpotent elements. Because of that, we get the following theorem, that the Kauffman bracket Skein algebra of surface I bundles over C when A is -1 is isomorphic to the coordinate ring of the SL2C character variety of the fundamental group of the surface. So we have an isomorphism here, so which is why Kauffman bracket Skein algebras are often known as quantizations of these character varieties. And the last thing that I would want to state is that if we replace this -1 by +1, we still have an isomorphism, but in that case, the isomorphism depends on the choice of spin structure on the three manifold. This is due to work by Barrett. So that's all that I wanted to say for today. Thank you so much.
Thank you, Rhea.
Yeah.
Thank you for the wonderful talk. So are
Thank
there
you.
any questions or comments?
I see a question. If we are considering links in a general T manifold, what do diagrams mean? What surface are we projecting the link onto? So this is only for surface I bundles. So if your three manifold is a surface I bundle, then we can project the links in the surface I bundle onto the surface, and then we can work with the link diagrams.
No, so I was meaning that for defining the Skein module, you used diagrams, right? The crossings were
right. No, they are in space. It's not easy to draw that on a plane surface, but they are in space. So they are not link diagrams. So the Skein relations don't represent link diagrams. They represent local relations in a three ball. Yeah.
Any more questions?
So I would just like to add that for complex roots of unity, so when you replace A with complex roots of unity, there's a whole new different field. So I did not talk about connections to quantum Teichmuller spaces and all of that, but when you replace A with complex roots of unity, you have very explicit connections to Teichmuller spaces and to, so there is a lot of rich theory over there.
Any more questions? Well, if there are no more questions, let us thank Rhea for the wonderful talk.